Hi everyone, today I'll be going over problem 7 of the CSM mock final. So the problem statement says, imagine the map of the Bay Area as an undirected graph. We only have one day to explore the Bay with so many places to see. Find our shortest path tree with SFO Airport as our starting point to visit every location on the map. Edge weights are not to scale. Resolve any ties alphabetically. So when we see a problem statement that mentions shortest path tree on an edge-weighted graph with a single starting point, we should immediately think of Dijkstra's algorithm. We can also see from a quick glance that part A asks us to mechanically execute Dijkstra's algorithm on this graph. To do this, let's first review the pseudocode for Dijkstra's algorithm. So I have here Professor Hilfiger's beautiful Comic Sans lecture slide here, as well as some notes that attempt to translate important parts of this pseudocode to plain English. Let's quickly go over this. First of all, let's define what this dist value for each node is. See that it's referenced quite a lot. So for any node v in the graph, v.dist represents the shortest distance from source node to v found so far. Note that source node's dist starts at 0, and every other node's dist starts at infinity, because initially no paths are known. And all of these dist values decrease as shorter paths are found, until finally settling at the optimal values. Now let's talk about the fringe. The main data structure that we use in Dijkstra's is a priority queue called the fringe. And this priority queue tracks all nodes that we have not visited yet. What does visit mean? A node is visited on the iteration where it is removed from the fringe. Each node is visited only once. Once removed, the node never gets added again to the fringe because its dist is already optimal. And the proof for this is out of scope for 61V, so for now you can just take it as a fact. When the node V is visited, each of V's neighbor nodes' dists is checked. And that would be this for loop here. And so that for loop translated to plain English would say, for each neighbor node W, if the shortest path from source to W going through V is shorter than the shortest path from source to W found so far, then update w.dist to reflect this newly found shortest path to W. All right, I know that was a lot. Hopefully that quick refresher helped a little bit. If you're still confused and have time, I'd recommend reading these definitions over a couple of times to internalize them. That's what I remember doing when I was taking 61V, and I found that once I internalized these definitions and invariants, then Dijkstra's overall made a lot more sense. All right, let's move on to actually solving 7.8. Okay, so you can see we have our pseudocode on the bottom left and our program state on the right. So I went ahead and already executed all the steps ahead of the while loop. All of that is just initialization, so we can jump straight into where most of the action happens, which is inside of the while loop. So let's go ahead and do that. So the while loop condition is while the fringe is not empty. So while there are still elements inside of this table, then we'll continually remove elements from the fringe and check their neighbors. So let's just run through this for this example graph. So the first line is we do a fringe.remove first. So that finds the fringe vertex with the smallest dist value and removes and returns it. So the fringe vertex with the smallest dist value right now is SFO with a dist value of 0. So we can go ahead and remove it and return it. And when we return it, you see that it goes to the variable v. So let's just write it down here. And let's also mark it on the graph so we know where we are. All right, let's move on to this for loop. So this for loop is iterating over all of the neighbors of v and performing this update step, this if statement and the following line. is an update step. So let's just dive right into it. Notice that the order in which we consider these neighbors doesn't matter. So let's just look at the first neighbor that we can see, which is San Francisco. Let's add that as our W variable. And to proceed, we're going to have to calculate this orange value here. So the orange value is v.dist plus weights of vw. V.dist is 0, and the weight of vw is 3. So the orange value is 3, and we're comparing that to w.dist. So let's try to find where w.dist is. W is SF, so w.dist is infinity. And we see that the orange value is indeed less than w.dist, so we set w.dist equal to the orange value. Let's go ahead and do that. Set w.dist equal to the orange value. All right, now we can move on to the next neighbor of V, which is Palo Alto. So let me just erase these things from the previous neighbor and move on to the next neighbor, Palo Alto. So we set W to be Palo Alto, and we again have to calculate this orange value for Palo Alto. So v.dist is again 0, and the weight of vw is this edge weight, so plus 2. And going back to the pseudocode, you see that again we're comparing the orange value to w.dist. So let's find w.dist. W is PA, so w.dist is infinity. The orange value is indeed less than infinity, so we set w.dist equal to the orange value, which is 2. All right, and now we see that SFO does not have any more neighbors, so we can go ahead and proceed to the next iteration of the while loop, which is. Let's also cross out SFO because we're done with that. All right, so the next iteration of the while loop. So we're back up to here. Vertex v equals fringe.remove first. Again, we're trying to find the fringe vertex with the smallest distance. SFO is already removed from the fringe, so we don't consider that. But out of the remaining elements in the fringe, we see that Palo Alto is the vertex with the smallest dist value. So we're going to remove Palo Alto, set V to Palo Alto, and let's just circle it too. All right, so that was this line. Now let's go on to the for loop again. The for loop again is checking for the neighbors of V. We can see that one of the neighbors of V is, or one of the neighbors of Palo Alto is Fremont. So we can set W equal to Fremont. Again, we have to calculate this intermediate orange value, and the result of that would be, so v.dist is Palo Alto's dist value, which is 2, plus the weight of the edge VW, which is 7. So the orange value is 9. Right, and going back to the pseudocode, the condition again is the orange value is less than w.dist. So if this orange value is less than Fremont's dist value, you can see it's infinity, then we update w.dist, which is Fremont's dist value, to be this orange value. You can see that the if statement does get executed, and Fremont's dist gets set to 9. All right, so what other neighbors does Palo Alto have? We can see that Palo Alto also has Mountain View as a neighbor. So let's go on to that. So Mountain View, we set W equal to Mountain View. That was an ugly M. Okay, W is Mountain View, and we again have to calculate this orange value. So v.dist is 2, and I got that from right here because V is Palo Alto, so v.dist is 2, and then the weight of VW is the weight of the edge between these two, which is 1. So Mountain View gets an orange value of 3. Again, we check the if statement. So the orange value less than w.dist? What is w.dist? W.dist is mountain, or W is Mountain View. So w.dist would be here, infinity. The orange value is indeed less than infinity. So we go ahead and update w.dist to be the orange value. All right, so that concludes the iteration for Palo Alto. Now we can move on to the next iteration of the while loop. Right, hopefully everything is making sense right now. The rest of this problem is pretty mechanical. You just keep on removing the fringe vertex with the smallest distance and then iterating over that vertex's neighbors and doing this update step, and that is encapsulated by this if statement. All right, we can continue on. So we're back over here. Vertex V equals fringe dot remove first. Look through the fringe table, see that the vertex with the smallest dist value, they're actually tied. So we have two vertices here that have dist values of 3. Now recall from the problem statement that it said to resolve any ties alphabetically. So in this case, we are going to take mountain view first. So let's go ahead and take mountain view and set V equal to mountain view. Circle mountain view. And so that was this line of the pseudocode. Now we're moving on to the for loop where we check all of mountain view's neighbors. The first neighbor that I can see is Santa Cruz. And so W equals Santa Cruz. Again, we have to calculate this orange intermediate value. V.dist is 3. So V.dist is mountain V.dist. Mountain V.dist is 3. So that's kind of covered up by my squiggle, but yeah, that's a 3, trust me. Okay, oops, I want that to be orange. Okay, 3 plus the weight of VW. The weight of VW in this case is 9. So we get Santa Cruz with a orange value of 12. So again, we're checking this condition. If the orange value is less than W.dist, W is Santa Cruz, Santa Cruz.dist is infinity. So if this orange value is less than infinity, which it is, then we can update W.dist to be this orange value. So we'll go ahead and do that. And that's it for Santa Cruz. Let's move on to another one of Mountain View's neighbors, which is Cupertino. Let's write that down here. And the orange value for Cupertino is going to be V.dist. V.dist is still 3. And the weight of VW is right here. And 3 plus 2 is 5. So we can run this if statement again. If this orange value is less than W.dist, W is Cupertino. So we go down here, we see that W.dist is infinity. The orange value is less than infinity, so we update it. Okay, and Mountain View, does Mountain View have any more neighbors? No, it does not. Okay, and that concludes the while loop iteration for Mountain View. And we can go ahead and cross that out. All right, next one is going to be, let's see, what is the fringe vertex with the smallest distance, or the smallest dist value? That would be San Francisco, right here, with a dist value of 3. So San Francisco is going to be our next V. So that was that line. And then again, we look at the neighbors of San Francisco. San Francisco only has one neighbor that is unvisited because we already visited SFO, and that neighbor is Berkeley. Okay, so W is not equal to Berkeley, and we run through this update step again, this if statement again. The orange value for Berkeley is V.dist is, so V is San Francisco, V.dist is 3. Plus the weight of VW, that's the weight of that edge, is 6. So Berkeley's value is 9. And we see that 9, the orange value is indeed smaller than Berkeley's current dist value. So we can go ahead and update that. Okay, and since Berkeley was the only unvisited neighbor of San Francisco, we are now done with San Francisco. So we can erase all of this. And move on to the next. Move on to the next iteration of the while loop. Okay, this is okay. So fringe dot remove first. The smallest vertex, or the fringe vertex with the smallest distance, is Cupertino with 5. So let's go ahead and let Cupertino be our new V. So Cupertino has 2 unvisited neighbors, Santa Cruz and Fremont. So let's just look at Santa Cruz first. W equals Santa Cruz, and let's calculate this orange value. The orange value is going to be V.dist. V.dist is 5, which I got from here. And then the weight of VW is 8. All right, so we have an orange value of 13. Okay, so this is actually the first case where we've met so far, where the orange value is actually not less than the existing w.dist value, because the existing w.dist value is 12 and 13 is not less than 12. So we actually keep SC's dist value at 12. So we don't do anything. Okay, and then we move on to the next neighbor of Cupertino, which is Fremont. And let's see. So we can start that here. And then the orange value for Fremont is going to be, again, Cupertino's dist value is 5. So v.dist is 5. And the weight of the edge VW is 5. Now Fremont's orange value is 10. Again, we notice that the orange value here is not less than the existing dist value for Fremont, because 10 is greater than 9. So we don't do anything to Fremont's existing dist value. And I think now would be a good time to point out that you should be noticing that the dist values only ever go down. So dist values only decrease, they never increase. I think that was one of the properties mentioned in the notes up here. Yeah, so you can see that every other node's dist value starts at infinity, initially no paths are known, and they decrease as shorter paths are found. So if you ever find yourself increasing a node's dist value, then you're probably doing something wrong, and I recommend going back and re-executing your program. Okay, let's see, where are we right now? We are on Cupertino, and we've already visited Santa Cruz, and we've just finished visiting Fremont. So we are now done with Cupertino. So let's go ahead and erase all of this. And move on to the next iteration of the while loop. So again, we come back up here. Vertex v equals fringe.remove first. The fringe vertex with the smallest distance is, I believe it is 9. And since there are 2 vertices with 9, Berkeley and Fremont, we're going to take the one that comes earlier in alphabetical order, which is Berkeley. So let's take Berkeley off of the priority queue and set V equal to Berkeley. All right, and now let's look at Berkeley's neighbors. What are Berkeley's unvisited neighbors? So we see that there's Oakland and Sacramento. Let's go ahead and look at Sacramento first. Okay, so W is Sacramento, and we again have to calculate the orange value for Berkeley and Sacramento. And so v.dist is Berkeley's original dist value, which is 9. The weight of the edge VW is 10. So that's 19. Oh, I forgot to circle. Right now we are considering Berkeley as our V vertex. Okay. So now we are looking at Sacramento, and since Sacramento's dist value is infinity, we see that this if statement does, or the if condition does pass, because 19 is less than infinity. So we are going to update Sacramento's dist value to be the orange value. Okay. And that's it for Sacramento. Now let's see what other neighbors Berkeley has. It's going to be Oakland. And Oakland's orange value is going to be v.dist is 9 plus the weight of VW is 2, sorry. And that gives us 11. So since the orange value is less than w.dist, then we update w.dist equal to the orange value. And that concludes the iteration for Berkeley. And we can move on to the next iteration. Okay, I think we're almost done, so hang in there. Let's see. So the next smallest dist is 9 for Fremont. Let's go ahead and remove that. And circle it. And let's look at Fremont's neighbors. So the only unvisited neighbor of Fremont is Oakland. And so let's write that down. Calculate the orange value. V.dist was 9. And the weight of VW is 4. The orange value is 13. Let's check the dist value for Oakland, w.dist. So w.dist is 11. And this orange value is not less than w.dist. So we don't do anything to w.dist. We just leave it as is. And we can move on to the next iteration. Since there are no more unvisited neighbors of Fremont, we can move on to the next while loop iteration actually. So 3 more to go. We're almost there. Let's check the node with the smallest dist value. Will be 11, Oakland. So move Oakland and set b equal to Oakland. And now let's see what are Oakland's unvisited neighbors. I think the only unvisited neighbor of Oakland is Sacramento. So w equals Sacramento, and the orange value here is going to be v.dist is Oakland's dist, which is 11, and the weight of VW is 15. And this turns out to be 26, which is not less than w.dist, or the current value of w.dist, which is 19. So since the orange value is not less than w.dist, then we don't do anything. And since Sacramento was the only unvisited vertex of the only unvisited neighbor of Oakland, we can move on now. So we just finished Oakland. And now we're down to our last 2. So the smaller of the 2, or the remaining vertex with the smaller dist is Santa Cruz. So let's set b equals Santa Cruz and remove it. And notice that Santa Cruz actually doesn't have any more unvisited neighbors. All of its neighbors, namely Mountain View and Cupertino, have already been visited. So we actually don't have to do anything for Santa Cruz here. And we can see a similar thing happen for Sacramento. So on the next while loop iteration, the only fringe element left is Sacramento, so we can remove that, set b equal to Sacramento, and notice that Sacramento does not have any more unvisited neighbors. So that concludes our running of Dijkstra's algorithm. And at this point, we can fill in our table here. Oh, I should have been updating the answer to A as I was going through the execution, but hopefully you can just rewind the video and see that the order in which we take off vertices is indeed the answer to this problem. All right, these types of problems are pretty tedious, but if you understand what Dijkstra's is doing and you get into the flow, then you can get faster and faster at it. So that is 7.A. All right, finally, we have true-false questions for 7B and 7C. Instead of trying to solve these using the giant graph that we had for 7A, let's look at a much simpler example and show a more general property of shortest paths. So 7B asks, if every distance increased by 2 units, would our shortest path be the same? All right, let's look at this simple graph up here. What is the shortest path from A to D? Well, there are 2 candidate paths. There's A, B, C, D, as well as AD. So you can see here on the side I wrote down ABCD has length 3 and AD has length 4. And ABCD is the shorter of the 2. Now, what happens if we increase all edge weights by 2? So let's just add 2 to every edge weight. We can see that ABCD's length becomes 9 and AD's length becomes 6. Now AD is the shortest path instead of ABCD. So what's happening here? Notice that because we're adding 2 to every single edge, each path length grew by, each length grows by 2 times the number of edges along that path. This means that paths that were originally short but have many edges have the potential to grow longer than paths that were originally long but have few edges. So the answer to 7b is false by this property. All right, let's go on to 7c. We can reuse this example up here. So 7c asks, what if we multiplied each edge weight by 10? Using our example up here, ABCD's length becomes 10 plus 10 plus 10 is 30, and AD's length becomes 40. So notice that ABCD is still the shortest path. Furthermore, notice that each total path length grew by a factor of 10 when we multiplied each edge weight by 10. This can be seen formally as follows. Let's define P to be an arbitrary path consisting of edges E1, E2, all the way up to some EC. So the original length of this path can be thought of as the weight of edge 1 plus the weight of edge 2 all the way up to the weight of the last edge. Okay, so what happens if we multiply each edge weight by 10? The new path length becomes 10 times the weight of the first one plus, and you get the idea, 10 times the last one. And this can further be simplified down to 10 times the original length of the path. Okay, so because each path length is growing by the same factor 10, their relative ordering doesn't change. So intuitively, if we have two paths P1 and P2, if their original ordering was length of P1 is less than length of P2, if we multiply each of these path lengths by 10, their relative ordering stays the same. So order of path lengths is maintained when we multiply each edge weight by some constant factor. Because of that property, 7c is true. Uh, the shortest path stays the same. All right, that concludes question 7. Hopefully this review helped, and good luck on your finals.